Now.
Okay.
Buenos días, bienvenidos todos a un nuevo webinar en la Expo Alemania virtual. Esta vez contamos con la presencia de FRAUNHOFER Academy, que una empresa situada en Alemania. Nuestro expositor es el doctor Winfried Hoffmann, quien dará su presentación en inglés. Y por favor, cualquier pregunta que tengan lo pueden hacer directamente en el chat que se encuentra en la plataforma. So, Winfried, we can start now, please. Now we can start.
Okay, so thank you, Rita, for the introduction, and very happy to be able to talk to you about a quite fundamental and important topic, namely 100% renewable energy. And that is for everything. So that means not only electricity, but also mobility and process heat and everything, everywhere and for everyone. So I gave you here some questions which you could easily answer at the end of this presentation. So let me just first introduce that what I'm giving to you now is a short summary of a lecture, which is the start for the Solar Energy Engineering Continuing Education Program, which you see here. And for everyone who would like to get some more information, you can look it up here. We don't go through it, so you will find then everything needed in order to have your start in such nice overview. So now this is to my person. My company is here Applied Solar Expertise. And as of today, I am consultant to companies and business angel member of the board of a company, and also still active in scientific boards like the ISFH in Hameln and the LR Institute in Oldenburg. And I'm giving lectures in Constance and at the university in Freiburg, what I was just showing. So let's just jump right into the situation as of today. What you see here in the picture is the primary energy, which is the left bar. And what you can see in brown, that is the fossil energy, coal, gas, and oil. And as you can see, in 2015, roughly, the total energy, primary energy, was a little bit more than 150 petawatt hours. So a petawatt hour is quite a huge energy portion. It's 10 to the 15 watt hour, and you can calculate it back, and you will get an idea about that. The worldwide electricity, which is seen in the second part, the secondary energy in yellow, electricity worldwide is a little bit more than 20 petawatt hours. So that just gives you an idea what a petawatt hour is. What you can also see in the primary energy picture in green, it's only about a little less than 20%. So we are still using most of our global energy coming from fossil. And that primary energy, that is changed to the secondary energy. I mentioned already electricity, and most of it is heat and process heat. And the gray part, that is oil for mobility. And then in the last bar in blue, that is the user energy. So that is actually what you would like to have. That is light, that is transportation from A to B. So, and in 2015, you see the summary here, we had almost 8 billion people. And very important, there's an inequity, because a quarter of those 8 billion people, they are using 3/4 of the prime energy. And for sure, that is something which we cannot have in the future. So as a result of this extensive use of fossil resources, mankind is executing a dangerous experiment. we are accumulating carbon dioxide with a consequence of global warming. That is shown here in that picture. In the last 50 years, the CO2 has increased twofold, from about 28 gigatons of CO2 in the 70s up to 52 gigatons CO2 each year in 2017, and it's still increased. Now, where is most of those carbon dioxide produced? And this is shown here for the various countries. And as you can see, the rising part, that is China. That is the electrification in China, starting in the mid-90s and quickly ramping up, as you can see. The second is United States, which just falls off a little bit, then Europe, and then you see the yellow part. And well, how will it develop further? So even if the Europe and US part would go to zero, and even if the Chinese would accomplish a very quick growth for renewables, there is still India, there is Africa, and many other places. And you can ask yourself, from those 52 gigatons, which I just mentioned, that most probably, looking to that, if you don't do anything, would further increase, as we have seen in the last 50 years. Now, if you take this picture here, and this is now the cumulative carbon dioxide. So in 2017, we have already 2,200 gigatons of CO2 in the atmosphere. And if you add each year the mentioned 52 gigatons, then you see the line increasing. Now, the scientists have told us if we would like to have a temperature increase limited to 1.5 degrees centigrade, like in the Paris Agreement, the cumulative CO2 is 2,800 gigatons. Now, if you look when this will happen, and that is the late 20s. So that would mean if we would like to stay at 1.5, then from 29 onwards, we have no possibility to add any further CO2. So the 52 gigatons must be zero. If you allow a 2 degrees centigrade, then you add a little bit more, and as you can see, but it will only give us a couple of further years to get then this really down to zero. Otherwise, we will really face big problems. So therefore, we urgently need an energy transition. And you see again on the left-hand side, the situation as of today, 2015, and what is needed in 2050, or maybe 2055. Then most probably we will have 10 billion people, and we have to stop inequity, as I was just mentioning. So we are asking that everyone on this globe should have the same energy quality as today's privileged level. So we further assume an energy efficiency factor of about 2.5. So just to give you an idea, if you change a light bulb to LED, then you will have an energy efficiency factor of almost 10. If you have an electric car compared to a combustion engine, then you have a factor of 3. So you can have many such examples. So 2.5 is something which is reasonable, but still quite an effort. And of course, that would give us the possibility to go to 100% renewables. As you see then on the upper part, the prime energy is only green, namely renewables. And the good thing is that when you have only renewables, then by definition, primary energy equals secondary energy. And what you also see here is a huge increase in electricity for the secondary energy. And still you have some heat and process heat. And the user energy is then quite interestingly increasing to a level which is twice the one which we have today. And for those who would just like to see how that calculation is done for the 150 petawatt hour secondary energy, I've just given it for those who would like to make a calculation for their own. Now, what is the energy content of renewables globally? On the left side, you see the technical potential, which is 80,000 petawatt hours. And interestingly, the yellow part, that is solar. The blue part is wind, and the red part is all other. And by all other, that means hydro energy, geothermal, biomass, tidal and wave, and everything. When you go from the technical potential to the sustainable potential, so that already takes into account that you need quite a lot of area for food producing and things like that. So that number decreases to about 3,100 petawatt hours. But still, you remember, we only need 150 petawatt hours. So that means that we have plenty of sustainable potential. And again, the split is 90% solar, 9% wind, and 1% all other. And in order to allow then in the future realistically to take advantage of local good possibilities, our planned supply for the 150 petawatt hours, we assume 60% solar, 20% wind, and 20% all other. Now, why is wind and photovoltaics in the future the dominating? First, as I just mentioned, they have a sustainable availability. The production of electricity on same area of land compared to biomass is already today 50 to 100 times more. So therefore, you should never use biomass to produce energy. So that should be always done by photovoltaics and wind. And that becomes even more visible when you go for electricity with an electric car compared with biodiesel and combustion engine. So on the same area, let's take the example, 10 square meter of photovoltaics, you can drive in Germany an electric car 10,000 kilometers. In southern regions, 10 square meter of photovoltaics, you can drive 20,000 kilometers. If you do the best biodiesel grow on the same area of land, you can only drive 100 kilometers. So again, as I was just saying, biomass should, for energy and transportation, should be forbidden in the future. Hydro, just to give you an idea, today we have 4 petawatt hours, and at the best, it will double at the end of the century. And wave and tidal, they have a local importance, but only available on few places. So as a result of the energy transition, there will be an industry transition. So these power stations, they will be like here, offshore wind, photovoltaic, and also the combination. And to give you an idea about the economics, there is in Great Britain a brand new nuclear plant, Hinkley Point. And the average price at the end of that power station, that nuclear power station, is more than 20 cents per kilowatt hour. When you would like to produce clean coal and gas, the cost is much higher than 10 cents per kilowatt hour. For wind and solar, already today you are at 5, and in sunny regions photovoltaic is already below 3 cents a kilowatt hour. And storage with large-scale batteries approaching 5 cents. So that means photovoltaic and wind, including storage, are significantly less expensive than the traditional ones. That means we have a big transition. Just to give you an idea about mobility, because that is something people are talking a lot about. You can either have on the left side an electric car. In the middle, you have a fuel cell fueled by hydrogen. And on the right side, we have air transportation and ships. Now, of course, the oil companies would most like the situation of a green fuel, because then everything could stay the same. And also the car industry would love it because they could still use the combustion engine. However, you will immediately see the 3 different parts. On the upper side, if you start with the same 100 kilowatt hours of green electricity on the left, with an electric car, you can drive 600 kilometers. If you make electrolysis to produce hydrogen and use the fuel cell and the electric motor, you are already almost bisecting the driving distance. And if you even go then with the hydrogen to methane and take then a combustion and gear, and even assuming only 5 liters per 100 kilometer, your range to be driven for the same 100 kilowatt hours is only 75 kilometers compared to the 600. And that is obviously immediately seen. So the combustion engine as of today, the cost is about $4 per 100 kilometer if you assume 5 liters at 80 cents. And the electric car, but with numbers, even including the distribution of renewable electricity, it's a factor of almost 4 cheaper. With the hydrogen, half the distance, it almost doubles, as you can see. And therefore, you will have for sure, for all those applications where you could afford it, you would use the cheapest way, and that is the electric car. And if you drive it with a green fuel, as just mentioned before, the price is very much the same as of today. So you will need the green fuel for special applications, like in air transportation, but for the cars, you most likely would use, whenever possible, the battery. The other is chemical industry. So here are just some examples how you could use green hydrogen in order to be introduced into the chemical industry. And I will just give you an example here, steel production. So globally, we are producing 1,800 million tons of steel per year globally. And that is associated with 2,700 million tons of CO2, so 2.7 gigatons. And that is accounting for 7% of the global CO2 emissions, so quite significant. Now, if you use hydrogen and also methane produced from hydrogen, and you make a direct chemical reduction of your iron ore, then you can dramatically reduce the CO2 emissions. And I could give you many more examples of that. So that just shows you how you are able to dramatically decrease the CO2 concentration which we are emitting today. So just a little bit about the photovoltaic market. So just take the message here that in the last 10 years, the photovoltaic market grew with more than 20% per year. So just to give you an idea what the industry was able to accomplish. And if you take the cumulative installations of photovoltaic, so the red part is the annual addition, just shown before, plus then what has already been installed in the years before, this increase of the cumulated number is 30% per year. And if you would like to go in the future, the next 30, 40 years, from today's volume to, in this case, 1.5 terawatt, then you would end up in the 60s with a number of 30 petawatt hour electricity. You remember, we need 150, so 30 is 20%. And you can just, by doubling the growth figures here, you can then make your own calculations what is necessary to end up with more. For those of you interested in technology, so that was the simple solar cell produced until the 80s. So a crystalline silicon with the front and back contact, and that was efficiency-wise ending up at 10%. So in the years after, we introduced passivation on the front side. So efficiency of the module increased towards about 18%. Having also the passivation on the rear side, these are the Perk and Pearl structures. Efficiency, what you can buy today, is approaching 22, 23%. If you then go to heterojunction back contact cells, you end up with the physical limit of a single junction solar cell based off of silicon with about 27%. Now, would that be the end? Of course not. You can put some more thin film solar cells on top of the crystalline silicon, which is already done today in industries and also in pilot plants. And with the two junction, you can increase efficiency towards 32-3%. And with a 3 or even more junction tandem cell, you can go up to 40%. And so as you see, there is plenty of space to be done in the future by research institutes and industry to further increase quite significantly the efficiency. So just for wind energy, so again here, the cumulative installations for wind, as you can see, they are about 17% per year. And just to give you an idea that also for wind energy, it's not the end of what you see today. So the machines, state of the art, they have about 3-4 megawatts per windmill. And engineers are working seriously on windmills, as you can see on the right, where the height of the Eiffel Tower is reached with the rotors. And these would then have 15 megawatts of power. So, and that of course gives also then again the possibility to decrease the cost for each produced kilowatt hour. Just an important point, we don't go to all the numbers here, but if I had told serious energy people 20 years ago that wind and solar will outperform nuclear power worldwide based on energy output, people would have called me really stupid. But that is exactly what is happening right as we speak. This year, photovoltaic and wind together, they will produce with 2.5 petawatt hours the same what today's total nuclear fleet worldwide is doing. Now that fleet goes down, PV and wind goes up. So that is what we definitely will need. That is only quickly telling you that the importance of having wind and PV, especially in Germany. So in Germany, as you can see, in summertime, we have most output of photovoltaic between April and August. And in winter times, obviously, we have less. Wind, it's just the opposite. So we have less in summer and more in winter. If you take the sum of the two, then you can have a nice smoothening of the energy output per month. So that is important, not to have a storage, a seasonal storage. And of course, if you go to more northern regions, you would install more wind compared to PV. And in southern regions, of course, you would add more photovoltaic compared to wind. So that is just to show you the importance of having photovoltaic and wind in certain areas for power production. Now, what is a disruption? And everyone is invited to look at Tony Seba. He has made very nice presentations on that. And he wanted just to give an idea what can happen very quickly and what normally people would never expect. That is a picture of the Fifth Avenue in New York in 1900. And the question is, where is the car? Because what you see is horse carriages. And where is the car? There is just one. Now, only 13 years later, the same picture, Fifth Avenue, New York. And now you can ask the question, where is the horse? And here is just one horse among the many cars. So in 13 years, that situation changed dramatically. And I'm pretty sure with what we have achieved cost-wise and for the environment, the same will happen with photovoltaic and wind, and combined with the other existing renewable energies in order to be able to combat the climate change, which I was just telling you before. So this disruption, that is a coincidence of several complementary breakthrough technologies. So today we have semiconductor for big data, and semiconductor, everyone knows, a gigabit chip costs nowadays $1. 50 years ago, that would have costed hundreds of millions of dollars. But only with today's prices, we are able to do the big data. We have optoelectronics. We have nowadays batteries available for energy. That together gives us a possibility to have electric mobility and also autonomous traffic. We have photovoltaics and wind, which gives us the possibility for producing with much less cost compared to fossil and nuclear, the future electricity, which you can change to whatever you need. And if you take that together, the offering of 100% renewable energy is really something possible. And that is what I'm convinced will be the reason when the finance industry has understood that situation, that we will have a really fast penetration for 100% renewable globally, and also solving the inequity, as I was telling you before. And just for those who want to read a little bit more about that, so I have written a book some years ago, but that is still readable and gives you more insight why things are happening in the industry and how is that done. If you would like to ask a question to me, you can use my email. So my first name Winfried at last name Hoffmann -ase.de, and I would be happy to answer any questions. So, but we still have, if I was listening correctly, Rita, we have, beside now the 30 minutes presentation, we have still time to answer some questions directly. Is that correct?
Yeah, that's correct. We have one question. Please, Lena, can you check it and tell it? Is it in German?
Can I see it, or can you give me the question somehow?
Of course, you have it on the chat. On the Zoom chat.
So where would I have the chat?
In der Chat, Winfried, eine Meinung zum Thema Fracking. Hat Herr Hoffmann eine Meinung zum Thema Fracking?
Okay, that's a good question. So fracking, as we all know, United States wanted to become independent of oil imports. So they made quite a huge effort to install many frackings. And as you may know, most of these fracking industries, they are some already bankrupt and some just before. Why? Because today's oil price, the international oil price, which is around $40 per barrel, at that price, fracking does not work because it's more expensive. So fracking can be done if the oil price is well above 50, 60 dollar per barrel. Now, at today's oil price, the fracking is just not working. But at the end, it will be what I mentioned before. Fracking only produces oil and gas. And when you burn oil and gas in order to produce electricity or move your car, you produce CO2. And that is what I was just telling, something which should be stopped as fast as possible. So we don't have many years. If you just go back to my first slides, at the end of this decade, so in the late 20s, we have reached the concentration of CO2, which will then have a 1.5 degrees centigrade increase. And even if you allow 2 degrees, it will only be 2035. So you have to stop not only fracking, but any oil and coal and gas production in order to be able to stop that.
We have another question. It said, how can we reach the energy market in Latin America regarding the use of hydrogen?
But first of all, you should use in the best possible way photovoltaic and wind, depending on the region, and in order to start to change the use of electricity and transportation, as I was just discussing. Well, hydrogen, as I was just saying, that today is produced from natural gas, which is nothing else than methane. And in the future, if you need hydrogen or methane for many reasons, and also the industry, then you can do that with photovoltaic and wind electricity. You make electrolysis to produce hydrogen, and hydrogen plus CO2 gives you methane, CH4. So that is what we can do all over the globe, everywhere, and also, of course, in Latin America.
Okay, that is all the questions we have until now. Queremos invitar a todos los participantes a visitar el stand de Fraunhofer Academy y resolver ahí todas sus dudas que puedan tener. Con mucho gusto todos los van a estar atendiendo, o en el mail de contacto que tienen aquí en su pantalla. Muchas gracias, Dr. Winfried, for your intervention. Thank you so much, and we left now.
Okay, thank you for listening. Goodbye.